So we're gonna talk about how a neural network read image. I think that's it. That's the goal, and it's bring us to the most not very important, not the most important, sort of very important areas in neural network, which is the convolutional neural network (CNN). Um, I'm gonna look for a data set that is very popular. Here it is. I don't get notification for some reason. Cannot hear anything. Yes. So we have all of this. Let me close the door real quick. Okay, we're ready. So for now, I'm gonna create what we just created last week, which basically the data loader and everything. And then we create a simple dense neural network, the things we have learned before, and try to make it work with the image. And we can see the problem with that, and then we go to the main goal, which is the convolution, and see how it can solve our problem. So that's what we're going to do. We have the data sets here. First of all, let's just take a look at those data set. As PD, we import a bunch of other things. Not PLT. It's a bit slow. DJ organizer, let's do that. So we have two different CSVs file. This one does not really matter. This two is important. The train is contain the input and the label, and the test does not contain any label, and it's not an actual validation that we did last time. This is for submission. So if you have a model, you can run it through this and then get the submission, and then give it to the Kaggle and see how well you're doing. So we're gonna use the train.csv. I'm gonna rush through this because I don't think we have enough time for this thing. We already did it already, so don't have to worry too much. We read that data frame dot head. As you can see, it's a weird data file. Usually, when we work with image, we don't usually work with CSV because storing image in a CSV is not good, right? You can see it's contain all the pixel. So what this basically means is that give you the label in the front, and whatever after this is the content of your image. So let's say I want to get the first image, and yeah, so the first input will have the label, so we have to skip that. So from this 0th column, from one column until 785, even though it's 783, it's include 0 pixel. That means there's 784, and we have to put 785 to because the last one is not included in here. Yeah, as you can see, it's just a big array of number. If you get shape, this is what it's look like. Just to visualize this, we can do a reshape and make it into a image. 28 by 28, I think. What is 784? Eighty 28. So 28 by 28 is the square image, and we know that this data set contains square image of numbers, and I did not talk about that, but we will see very soon. So image show, this is your number 1. If I take the next number, maybe it is a 0, the next it is a 1 again, a 4. So you get the idea. This data set contain a lot of image of handwritten digit um, between 0 and 9, and our job is to classify which number it is by just looking at the image. So let's create the data loader. I did this last night, so we're gonna go through this again. A data loader is to load the image, obviously. So let's call it MNIS. Usually with this simple dataset and a bunch of other dataset, we don't usually create our own dataset class. We can use some online one, or there's some built-in, but for the sake of learning, we're gonna go through it very quickly. Um, from torch.data.utils, and the data loader doesn't have that. Utils, always get that wrong. We have to extend the dataset class and define the constructor. This take in the data frame. Actually, let's take in the data frame. Or actually, take in the input, all of the input and all of the label that we will split. Let's split it here. So we're gonna use the sklearn thing. Import split OS. So we can split it. Actually, the data frame dot values, as we talked about before, is that all of the row are the input, and whatever from 1 to 785 is the image input, and then the 0th is the label. But the function itself can split the data, can split this thing for us, I think. Oh no, we need the actual input. So for all of the row and for all of the pixels, so A4, A5, that is our X for our input. Data frame dot values, all the row and the first column, the label column. We want it to be 80 and 20%. So that's how we split it. So the split should be the train X, test X, train Y, test Y. Let's look at that. sklearn model selection. You can see the screen and everything. Okay, I hope I'm sharing. Train test. Okay, we get it. We got it. We got train, we got test, train, test. So this is just splitting the data frame data into train and test, but then again we have to use this to load them, and the x is the whatever this is, so it could either be the train or the test, so it's generic that we can use it for anything. So self.x is equal to x, just gonna store it and do nothing about it. The length function, I think, or maybe we have to do this. We just return the length of the x or y, does not really matter which one. Then we have to implement the get item, and this taking an index. We don't know which one, but it is an index. So our dataset return two thing for this specific task is the image and the label. So to get the image is just take the x at the index. So to test that out, because I'm not too sure either. So let's say the index is 0. What does it look like? It is an array. And if you do shape, you got 784. So that is our input. And this is a NumPy array. So we want to convert them into tensor. Torch.tensor on the image with the data types of float 32. After we get the tensor, we have another things that we want to deal with. Right now the image is just a one-dimensional array containing all of the pixel, but the image should be in the forms of an image, obviously a 2D array. So if you train X, let's say we take the first one again, this is just testing. I spelled train wrong. Same thing as before, it is now tensor, but we could do some reshape this. So what's happening is that we want to change this one-dimensional array into a 2D array. We could use something called view, give it a shape, so 28 by 28, and it would do that for you. Usually we have another thing that we want to do is the channel, the color. So in our case, this is grayscale, like grayscale. So in the case of RGB, you would have three different channels, the RGB color of each pixel. So the image is 28 by 28, and each of them has three different things. Now, in the convention of PyTorch or a bunch of other libraries, that we put the channel in the front. So we have three different channels, and each channel is an image. So this is how we do, how we think about it. But in the grayscale case, just one. Right now we have the tensor that look like that. So we're gonna do it directly here. Dot view 1 by 28. Got the image. Now we need the label. So the label is y at the position index. The same thing we want to convert into a tensor. But for the label, it must be a long in integer 64. I don't think we have to shape this. Let's check it out. Let's delete all of this. Train y at the position 0. It is a single number. But if I convert it, it is same thing. And if I do shape, it doesn't have any dimension in here. So I'm not sure if that's gonna be a problem. let's just ignore that for now. Let's keep that in mind. So our label doesn't have anything. It is a tensor. It doesn't have a dimension, but it is a tensor of a single number. So we will see if it is a problem. So we're going to return both of them, image and the label. And then we're going to create a data loader for this. I got some call. Hold on. I'm so back. All right. So we have the data set. We need a data loader. First of all, let's create the data set for both of them, the train and test. Train data set is your data set, MNIST data set, and it need the the array. So train X and train Y. We have two data set. Now we need the loader. We're going to use their data loader. Put in the data set. In here we have a few options. First of all, shuffle is very important. And the next thing is batch size. So what is the batch? Batch size, we're going to create a 32 for each of them for now. We will see what's the difference later. For the test data loader, I'm going to use this. No need to shuffle. Another thing that we should do is to use transformation in the data loader. So we provide a function to transform your input. Now we already transform it into tensor here, but usually in image processing, we do something called augmentation, which basically apply noise to your input for training, only for training, so that your model doesn't overfit. That is a solution to overfitting with image. It's basically try to make sure that your image is a little different every time. So that is what we can do, but we're not going to do it here. We're going to go with a simple image data loader and see if it actually load. Train. If I do this, we could do make it into a iterable, call next on it. And since the data return two thing, a tuple, we can get the test image and the test label and see what it look like. Dot shape. So as you can see, we got a batch. So 32 is a batch. 1 is the channel height and then width. So it's not width height, but we don't really care. Just whatever that is. So that is for the image, and for the label, let's see what it looks like. It's also a tensor with 32 different labels. So it should be fine because the data loader combined them into a batch, and now we have something instead of a zero-dimensional number. So just a few other things that we could do is to visualize any of this. Um, if you want, the image is a batch. So if I get the first one, I got the channel and the image itself. And if I want to visualize this, we can use the matplotlib.image show again. And we have a problem. The problem is, even though the convention is that the channel is in the front, matplotlib really want the channel to be in the back. So it's a bit counterintuitive intuitive in this case. So we just need to move it around, not view. We use permute. Permute is to move the index around. So initially the index is like this, but if you want to move the first one to the end, you just put it at the end. I want to check if it's still here. Wait, Alfred said something. Okay. Yes. So that's our image. We permuted a bunch of things. You don't have to worry too much. We can check that out later. But yeah, we got the image. We show it. Bada bing, bada boom. But what if we want to show the entire um, batch? That is what we can do. And I don't know how to do that. So PyTorch, I think it's called MakeGrid. So there's a function in Torch Vision that we can use. Uh, like this. If I take this, we import. I hope the noise is fine. MakeGrid. So this is a different library. It is from PyTorch, but Torch Vision is specifically for image processing. Utility import or MakeGrid. Just take a bit of time. Now we can make the grid. I can put the image in here, the batch image. So you see, there are three channel in the front, even though our image is grayscale right now, and whatever this is, we don't really know. So let's see if the size match. So at 32 by 1 by 28 by 28, and this is 3 by 122 by 242. The shape is different. So this one has some additional value, so it is a bit larger, I think. Is it? 25,000, 88, I cannot speak, 88,000. So I guess the make grid just just duplicate your grayscale image into three different channel, no matter what. And we have to do the same thing. We have to permute it, 120, and then we display it. Matplotlib image show, and you get all of your image in the batch. Now there's something we also need to do. Um, I know there's a lot, but let's just hang on a minute. We show the image. Let's put it down here. One thing that is important is we need to normalize the value. And I'm not going to do anything fancy. We're just going to put it between 0 and 1. The reason being because right now, if I do image.max, it is 255, which is the maximum value of the pixel. So we need to make sure it is between 0 and 1. And to do that, what we can do is that we divide this by 255. And hopefully that put it between 0 and 1. And you can also see the image a bit smoother. For some reason, I don't have an explanation for this, but after the normalization, everything should be the maximum of 1. So that's that. Um, Hang on a minute. Okay. So I hope this is not confusing, or maybe it is, but we're gonna keep going. Excuse me. We're gonna keep going regardless. So that was a lot. Where are we? We got a data set, we got the data loader, we got everything. Let's create the training loop. Let's do it. Um, Taking a model, taking the loader, taking the loss function, and taking the optimizer. Um, we loop through our loader. So for this will give it the images and the labels, basically a batch of them, the loader. So you do a for loop over this, it gives you batch at a time. So the model technically can work on a batch. It's supposed to work on a batch, and you can get your predictions. And then you can calculate your loss by calling the loss function on your predictions and the labels. And after this, we can call our loss.backward. Actually, before that, we have to clear up the gradient, and then we call step. Follow this part. We loop throughout batches. We predict, calculate the loss, optimize it, and we do need a few other things, which is the total loss to keep track of the average later, and the total batches, which is the length of the loader. And that means we can get the total loss dot item. Dot item is just to move it from a GPU, a CPU, a GPU to CPU, I think. Um, if we use GPU, we don't use it now. We're not going to use it. Can return all of this. I didn't know we have holiday around here. Uh, model.train. So we want to make sure that we put the model into a training mode, and there's something we can explain about this later that is very important. For now, this is your training function. For the testing, very similar. Actually, let's just do this. Test taking the loader, the loss function, no optimizer. We put it into eval. Everything is the same except this part. It's gone, and I think that's it. Also, one more thing is so that it doesn't do any gradient. When it go forward, it doesn't have to worry about gradient descent, so it's a bit faster. So that is the train and test. I hope that is correct. So we will see if it is actually correct or not. So let's build a dense neural network to work on this thing, and then we figure out how to solve it with convolution. So hopefully 2 hours is enough for this. Create the den, let's call it den vision. It extend the neural network module, the constructor, then we create the layers. So I'm just going to use the sequential function so that we don't have to create a bunch of layers separately. We just use it here. Excuse me. It's getting worse for some reason. So dense layer is just linear, but the problem is our image. How do we deal with image in this case, right? There's a lot of questions, so let's do this. First of all, we do the same thing as before, the iter on the train loader, and the next. Wait, actually we already have that here. So test image dot shape. So you can see batch, don't worry about it. The input is a bit weird. It is 3 dimension. We got one channel 28 by 28. How do we feed this into a linear layer, right? One thing we could do is to flatten it out. So if you call flatten and then give it a dimension to flatten it. So we have 4 dimension, but we're not going to flat it on batch. We flat it after that. So a batch, each of those element in the batch is a flattened array that we want. So we have to tell it where to start flattening it out. Start dimension is after this. I think. So let's see. Yep, so we have a batch 32 of one dimension array. Even though the input, the dataset itself, already flattened it out, as we seen already, we're not going to do that. We make it into an image first, and then we flatten it using inside the model instead. The reason because when we get to CNN, we don't actually have to flatten it yet. So this is what we can do. If you flatten it out, that's the idea, right? So if you have an image, where is this? Oh damn, what's happening with my voice? An image, to feed it into a linear layer, you flatten it, and that flatten basically means if you have a bunch of pixels, let's do this, take a bit of time. I don't know what's happening. Yeah, so you have your image. Let's group them. Flattening this image basically means you take this first row. It will be like this, and then the next row will continue just like that. So that's what flattening is about, and we essentially got a big one-dimensional array of your image. So that is what we could do here. So the first is still linear layer. We will flatten it while we doing the calculation later on, because flatten is not a layer on its own, even though there might be class that we can use, but we're just gonna do this. So the linear layer will take in 784 pixels or features, and let's create a few layers for this. The next layer, let's create a 180, 128. Let's use ReLU for the activation. A few layer, maybe 128 to 64, and then 64 to 10, because the class, there are 10 different classes, so we want a probability for that, even though we don't use softmax, as we explained already. So that's our layer. To calculate it, simple call, implement a forward that take in an input, and the output is your layers. So self.layers, call it directly on the input, and then return it. And I think we forgot to flatten it. So x is x.flatten is 1. So we flatten it, we put it into the layers and get the output. NN is not defined because we forgot to import it. Import it. Create a model. Let's create it. Model is the dense vision, and the loss function, we're going to use the cross entropy because it is a classification problem. Forgot to call this, so call the parent constructor. The optimizer, gonna use Atom, so torch.optim Atom. Give it a parameter, right? So I think we don't have any errors. Let's just go straight to training. For I in the range of 10, usually image processing, if you go beyond this, your model is not working well. Maybe you do need to sometime in the complex task, but in this task it's so simple. Uh, so let's keep track of train losses, test losses. Call the train function on your model, on your train loader, on your loss function, and on the optimizer, and this gives you the train loss. Same thing for tests, except we don't need the optimizer, and except we use the test loader, and this is a test loss called test, by the way. Now we append it so that we can look at the loss over time. Easy to debug our problem and see if we have any problem with that. Test losses. Let's print something out. Epoch is I. Train is your train loss. Test is your test loss. Let's run it. Train loader is not defined. I think we call it data loader. Given 4, what is that? Model loss. Huh. 1, 2, 3, 4. Did I get something wrong? One, two, three, four. What? What if I do this? Okay, that's not right. Optimizer. Let's run this. I think we forgot to run. Maybe we do. Oh, redefining train. That is Python. So Python. Okay. Assume everything is working fine. Let's see. So this is a bit slower than last time. Not a bit. This is so much slower than Iris dataset, because it is image, and this is how usually you have to go through when you train a data neural network. So you just sit here and look at the number all day. So most of the task we just did is to prepare your dataset and everything. We got our model that is a dense layer, and we flatten the input, feed it in there, create a model, and do the training. So we got it like what, 0. That is decent. Let's do some plotting and see. And this is where also the overfitting usually happen with this data set. Oh, did I just... Yeah, that is a big mistake. Let's train it again. Another thing I want to do though is to get the trainable parameter, because we want to do some comparison with the actual CNN and see how different the number of parameter affect the model. And spoiler alert, the CNN has so much smaller trainable parameter, but it is better. It works so much better than this. So get number of parameter. I think we can use this. It's for trainable parameter. Okay, let's run this. As you can see, it's going back up. That is overfitting. The model is the training is going down while the test is going up. But regardless, the trainable parameter for this is 100,000 something. Now if we increase the things, let's do that. 256, 256, 128. Let's put in another layer. And we're just gonna wait through that again. And there's a lot of things we could do to prevent overfitting, even with this bad network. Is data augmentation that we already talked about, is to apply some noise to your image. Basically shift it around, move it a little bit, rotate it around, so that every time the same image is not the same for the network. It doesn't look the same every time. That is one thing. The other thing is to apply dropout, something called dropout. Basically in one of this layer, or maybe all of them if you want, you disable the parameter, the training parameter, half of them or some percentage, so that the gradient, when it's flow back, the model is forced to use a different path every time, so it doesn't memorize all the time. It's a bit generalized, so you can see it's pretty decent if you increase it, but if we keep going further, increase it a bit bigger, overfitting is even serious. So I'm just gonna implement the dropout and see what it look like. I'm not gonna run it because it take a long time. So dropout just look like any other layers. Give it 0.5 mean 50% or all the time, every training. So after this layer to this layer, I'm not too sure how exactly it work. Andrew mentioned that it is just a mask. So your input pass through this, some of them pass through a 0, so it's multiplied by 0, and it doesn't pass through at all. So, and when you do this, it is important to set your training, your model into a training mode and the validation mode accordingly, because validation or testing, you don't really need dropout for testing. So when you do this, your model know exactly to disable this layer specifically. So that is what you could do. Yeah. So you can see it's pretty decent. The number of trainable parameters is a lot, 200,000. That is not small, consider for the simple task of recognizing digits, and comparing to what we're about to do, it is so much larger than what it need to be. So what's happening here? Um, let's do some visualization. Let's do some whiteboarding. Um, let's duplicate this. So this is what's happening, right? You have the image, you flatten it out. By the way, this is not the exact same number of pixel, if you haven't noticed yet. But we flatten it out. You have all of this nodes, the layer that we had before. I don't know why it does that. Delete that immediately. And then the next layer, we essentially either increase it or shrink it down. It does not really matter which one. But what's happening is that you connect every single pixel from here to everything else in the next layer. So to know a single thing about this node, you have to look at all of the pixels from the input. So it looks something like this for all of them. So I'm just gonna go through it for all of them, right? So just a few more. Blah blah blah. Oh, okay. So essentially what that means is, for a single pixel, if we look at it up here, it just look at the whole image at the same time, and that is not ideal. Now, why is it not ideal? Let's get into that. So this problem is something we call a curse of dimensionality. Yes. Any questions so far? Gotta check it out. The curse of dimensionality, which does not explain what it is exactly, but it sounds cool, so I'm gonna put it in here. What it means is that it's gonna take a look at the whole image, and like last time, when we talked about neural network, we sort of look at it as a feature extraction, right? Now, if we want to detect or classify class of number, basically either it is a 1, it is a 2, 3, and so on. For us human, we might not notice this, but sometimes we look at uh, lower level features such as line. So let's say a 9 has a circle in there. So in this layer, we might try to detect whether there's a circle or not, and whether there is a vertical line or not, whether there's a horizontal lines or not. So this is what we could think of neural network, right? You have an image that has a bunch of pixels everywhere, and you try to extract them into this format, and then you do it again and again and again until you reach your desired classification at the end. But it doesn't happen this exactly, but it is simplification, right? You have to remember that. But what's important is that in between we have to do this feature extraction no matter what. So if we think about what this node over here, that single node over here does, is it's basically trying to identify one of this shape. But here is the thing about the image. For any other problem, it might be not not really a big deal, but for image, a circle, if I can take a, can be either here, the same circle. It could also be here or anywhere in this image, right? So let's say a 9 is here or a 0 is here, and the next image, the 0 is all the way down here. So the model now have to deal with the position of this shape. So what we can think of with this problem is that multiple of this node, multiple of them might be trying, that is a hypothesis, and I try to visualize this and it doesn't actually happen, but we could think of it this way. Multiple of this trying to detect the exact same types of feature, but just on a different areas. So this node over here has a set very similar sets of parameter to this node over here. It just that sets of parameters is shift a bit to detect the circle at a different position, right? So that's what we can think. It's trying to identify the same exact same feature just on a different location. So it is not really a big problem because the initial idea of neural network is that it's because we don't know where the feature is gonna be like and where the combination is, so we connect it to everything all at once no matter what. But that give us the problem because the shape itself, you don't need to look at the whole image to know whether there's a circle up here. All you have to do is to look at this area and see whether there's a circle here or not. And then you have to look at this area down here to see whether there's a circle down here. You don't have to look at the whole image all the time, right? So the solution to this is pretty simple. I already talked about it. I just said that already. What we could do, instead of looking at the whole image, let's just look at a small chunks of that image. Why does it keep moving that? I need to lock it. Yes, it's locked. So instead of looking at the whole image all at once, we can just, I cannot move this. What's happening? I hate this. I don't like this. Wow. I have no idea. Cannot even delete this. What's happening? Okay, it is back. It is not back. Okay, yeah, so instead of looking at the whole image all at once, we look at a small chunk. That would reduce the problem of too many trainable parameter for this node. But that doesn't also mean that we should do the same thing for a different node. So for the next set of thing, we don't have to use a different sets of parameter for the same types of things, right? So we still want to detect circle. That means we don't need a different set of parameter to detect the same exact thing that we already detect up here on the top left. I hate this so much I cannot select it. Please allow me. Get out of the way. Oof. Tough job. Yes. So the first thing, shrink it down. The second thing, reuse your sets of parameter that trying to detect the exact same thing. So if we're trying to detect the circle, let's just use the same set of parameter, detect the circle everywhere in this image. And the way we do it is this. You just put it up here, the next one, the next one, the next one, and move down. Boom, boom, boom. Right? So that is the idea of CNN, the whole idea that we just went through. Again, to summarize, the problem, too many things all at once, and there will be multiple nodes that will try to detect the exact same thing just on a different location. And even though that is fine, it look at the whole image too much and the parameter is always different. So for this this specific circle over here, it is a different sets of parameter. This circle over here, it uses different sets of parameter, so it's too much. So instead of doing that, we don't do that. It's simple. You reuse the number parameter, the parameter that detect the exact same thing. So when we get to convolution itself, we should get started with their terminology. So instead of dense layer, I am not so mad about this. Okay, it's gone. This is your image. Your parameter is in a form that we call kernel. So this is your kernel. The size is a good question to ask. The size of your kernel. Usually it is 3 by 3. It could be 5 by 5 or 2 by 2. Does not really matter which one, but 3 by 3 is always the good number. And the way you use this is use this exact same thing that we talked about. You overlay it over your image, and according to the neural net formula, the linear combination is that you do this. You take the pixel that it's aligned with, you multiply with the you take the weight. So this is basically a bunch of number, your weight, right? Trainable weights. And you align it with the pixel it is on, so it's multiplied and then you sum them up together at the end. And this whole overlay thing will give you a single number, some number. So if you do this to the whole image, it will give you a new image of features, activated features. So what that means is that if you overlay this, you got a pixel. You overlay this again, you got another pixel out of it, again and again, and then boom, boom, boom. So the output image is a bit smaller because you don't take into account the edge. So it would look something like this big. Not again. I will move it out here. So yeah, that's what's happened. You applied the kernel, you got a new image. And that new image basically tell whether that the feature this kernel is trying to extract. So let's say this is extracting circle. So if there is a circle up here and down here at the same time and here at the same time, the pixel that correspond to that area, because it just extracted from that area, right? It will be activated. It will be activated here and here, right? So that is what's the feature image. So I like to call this feature image. Image of feature, or yeah. So I'm gonna use this term a lot, feature image. That would be a lot. So that's how convolution works. You have a kernel that is basically a small set of weight that you reuse on the whole image, and it gives you a new image. And before we continue, this kernel doesn't usually extract circle directly, because the kernel, let's just search it up. The layer of abstraction is that it doesn't actually be able to extract circle at all, but what it could do is extracting edges. So at the first layer, it will be able to extract something like an edge, something like that, right? If you take a look at the kernel itself, this is like a predefined kernel. If you know the predefined kernel, you could extract specific types of edge you want, and there's a lot of this that you could do. But the main idea of neural network is that we don't really care about what kernel it is. We're just gonna let the model learn, and it will learn whatever it need to extract, whatever types of feature it need to. And then you use it again, not these sets of kernel. You use a different sets of kernels on a different layers, multiple of them, to extract higher and higher ideas. So it's back to the same idea as this, but using convolution. And instead of dense layer, you have kernels. Okay. Nobody's still here, just Karina. But yeah, so that's what's happening. It's just feature extraction with a bit more control and focus. It's focus and reuse, and the reason you reuse it, it's enforce your model. The backpropagation force your neural network to learn the exact same feature all over the image. So it is focused and everything is a bit cleaner rather than everything all at once, just like that. So that's that. The next step is to learn that there are multiple kernel in a single layer. So you don't usually just extract a single image out of it. You extract multiple of them. So again, your image, you would use multiple kernel. And this assuming that the image is the grayscale, so there's only one channel, right? But if there is multiple of them, let's say RGB, this is R, G, and B, you don't really have to worry too much. But before we continue, let's just do grayscale for now. Right, so you have a kernel. the image applied to this kernel give you a new image. So I'm gonna duplicate this. Put it up here. So that is one kernel. So if we use multiple of them, that is different sets of kernel again. Let's use different color. It will give you another image of that kernel. So this might be extracting all of the vertical edges in the image. So the blue, let's say, it will learn. We don't really know, but it will learn that I need to extract vertical edges everywhere on the image, right? So the image will be a bunch of activated node about the vertical edges. And then this kernel over here might learn about horizontal edges or some corner scenario, shenanigan, and so on, diagonal and so on. So it could be anything, right? We don't really care. We're just gonna let it learn. So the same idea applied. We let it learn no matter what, but we just shrink it down a bit and make sure that it is focused on the right task. So 2, we could have more. 3, that means we have another image out of this, right? It might be a bit difficult trying to visualize this in the first place when you learn about convolution, but this is how I like to do it. You have 3 different kernel. It will be different sets of image in the output, right? Now, what's happened when you have an RGB image? Or worse yet, the next layer you have multiple other kernel again. Because usually we don't just use one, we use multiple of them. And now that we got to this point, we don't just work with a single image anymore, we work with multiple of them. So let's just give it one more. Right? So how do we deal with this scenario? Something about confusing about convolution is that we think of the number of channel as a number of kernel, but in reality the number of channel is this number over here, is this thing. So if you say a layer has a 4 channel, that means whatever happened, it will give you 4 images, 4 image feature images. That's the word I was looking for. So we don't really care about the number of kernel, even though it need to be a specific number. Whatever happen, it will extract that number you need to. So if you need 4 different images, feature images, it will give you 4 different feature images. So in the next layer, if you need 5 different feature images, what's happened is that it's essentially duplicate this. Not duplicate, it multiplied the number of your kernel. So the input has 4 of them, 4 different feature image. So you multiply, you use it once, you use it again on the next image, you use it again on the next image, and then you use it again on the next image, and all of this give you 4 different image, and then you add those image together. So you add pixel by pixel, and that give you a single image at the output. That's how you do it. And then you do the same thing, you do the same thing, you do the same thing, and then you do the same thing for all of the output. So this is what we call a subkernel, and I did not know this when I first learned. I come to discover it in the hard way, but it turns out it's not a single sets of kernel all the time. It's multiply, and they're all different, and then you add them up. So all of this, no, actually the color is not make any sense. Yeah, it does not make any sense, but you got the idea. There's 4 of them that apply to each of this, one of this, and then you add them up at the end to get one single output, because there are 5, so that's how it works, right? I hope that explained it well, the idea of the kernel. So what's important now, let's just go through the RGB scenario. So if you want 4 different sets of feature at the end, you would not need just 4, you need 4 by 3, so there will be 3 of them. Each of this is for RGB, so you apply to R, get the image, G, image, B, image, and then add it up all the image up to get 1. So that's that. So to summarize this, we will implement this, by the way. I just want to make sure that we understand the point. The point is neural network is the dense layer is bad for image because it look at everything all at once, and some of them might trying to do the exact same thing with just like the other but on a different area, and that is bad. So we shrink it down so that it look at local image, local areas. That is localization in neural network. So you localize it and then you reuse the same sets of parameters so that you enforce it to learn the specific feature you want it to do without having to relearn again and again multiple times. And you do it again, the next layer and the next and the next. So that's how the convolution is in neural network. So we're gonna try to implement that. We're gonna go fast. We only have 30 minutes left, and should not be a big problem. So CNN vision is extending the module. Excuse me. Yes. So PyTorch gives you a thing that you can use. So I'm gonna create the same layers using the sequential, and there is module called conv2d. I forgot what 2d is. There conv3d, conv1d. I think it's this thing. So the kernel is for 2D images, so you could even apply it to a 3D thing or just 1D. So convolution doesn't just work with image, it could work on any types of input that need localization. Alright. So conv2d, it need the number of feature input, number of channel. So not the number of pixel, because it does not really care how big your image is, because it's gonna reuse it all over the image. So our image is grayscale, so it has only one channel, the brightness. So we use 1, and the next is the number of features output you want. So let's use 64, right? And we still be able to apply activation function if we want to. So usually we use ReLU, and then we do this again and again. So let's say this is 64, it must match with this, and then it gives you 32, and then 32 to 16 probably. So that is convolutional layer, and just to visualize that, it would look something like this. So usually you have all of this kernel, right? And it will give you a set of image output, and then we apply something called max pooling, but we're not going to talk about that yet. Then we apply the convolution again, just like we talked before, using the subkernel method by multiply your kernel to occupy all of these features input, sum that up so that you get the features output you want, and as we go the image gets smaller and smaller. If you use max pooling, it gets even smaller by a quarter or something, I don't know the exact term. But the problem now is the convolution only gives you images. It is even worse than the input itself. It's not just a single image, but multiple features image. So how do we classify that, right? That is our question today. After we do the convolution, how do we take this and try to do some classification, trying to determine what number it is? So this is pretty simple. What we do is, it is totally fine now that we what is that? You flatten it. So now it is not really a big problem anymore because we already extract a lot of things. So it is okay to flatten your whole input out into a single dimensional array so that you can apply it to the linear layer. So now the linear, you just need a single linear layer to work. No need for multiple, and the localization problem is not really a big deal anymore. At this point, you just need to know how many circles there are, how many, or not how many, if a circle exists or not, and so on. So you go, if you have a lot of layer, it will do that technically, or hypothetically. So it's not really that way, but you could do that. That's what's happening. Now that we have that, we can finally use a dense layer to do the densely classification lead thing. I cannot speak as the time goes on, so I hope you don't mind. So that's what's happening. We need to know the number of pixels from all of this so that we can use it in a linear layer. So at the end, I'm not going to use linear there, I'm going to use it here, and n.linear. And we don't know the exact number of input for this layer, so gonna ignore that for now and do some experiment. So create the forward that take in self and next, the input. And I want to know what is the exact output from the convolution. So self.layers on the input, give me the out, and I want to return it so that I can see it. So this is, I forgot the comma, the CNN vision, and I'm going to create that model. That model, and we're going to create some test input. We could use our test image up top. Actually, we could do that, but another way that you can test this if you don't have any proper input or the input is too big, we can test it with smaller one or similar thing by do this torch dot random to generate some random number with some shape that you want. So we hypothetically put it 16 per batch, a single channel, and 28 by 28. So this is our testing image, and if I put it into the model, we will get something out of it. And we're not going to look at the whole thing, we're going to look at the shape instead. Missing one argument with the kernel size. Oh yeah, we forgot about that. So the convolution need a kernel size. For now, we're just going to use 3 by 3. We're going to take a look at the good model out there and see what they use. All of this is 3 by 3. Okay, so as you can see, 16 is not good. Use 32. So a batch of 32, ignore that. What we have is 16 images of 22 by 22, and this, we could take a look at any one of those if we want to. Test image, test input. Take a look at the first one, move the index around a little so that we put the channel at the end rather than the beginning, and then show it. And it's just an image, a random image, because the input is also random. The model hasn't learned yet. It is also very cool after we train the model, so let's do that later. But yeah, the most important thing is that the input image is now the features is now 22 by 22, right? It shrink down a little because of the way we convolve it. I want to apply something like a max pull just to demonstrate what you could do. Max pulling is this: you have your image. So let's say this is your feature image that you got from convolution. Max pulling 2D with a 2 by 2 kernel, not really a kernel, is that you look at a chunks of 2 by 2 areas. So you look at that and you take in the maximum value out of each of those. So whatever is the maximum, you take out of that. And as you can see, it shrink down the whole 4 pixel to a single pixel. So this is just for performance, and there might be some other reason that we needed to, but most likely the image gets so much smaller that the computation is so much faster, right? So max pulling 2 by 2 from this, after this, and after this. Run that again and see what's the shape. Okay, we essentially shrink it down to 1 by 1. So that's what we could do. That's not what we could do. That's what we have. 16 different images, and each of those images is just a single node, and that is weird, but that is fine. We're going to create a dense layer that take in 16 by 1 by 1, and the output is 10 different classes. Excuse me. So before we return out, let's apply that self.dense on the out, and I think that's gonna give you error because we need to flatten out. Because this is a different images. We don't want that. We want a single vector. So you flatten out starting from the dimension 1, from this dimension on, because the batch we don't care. Now we get 10 classes. So that seemed to be okay. Everything is going great. Let's turn that off and train it. Let's do this. Let's reuse the whole thing. It's also cool if we plot the loss. That take a long time. What's happening? Let's just wait. Also, maybe you can run that. That is very slow. So we want to use some GPU. This is the point where I need to do some optimization. Otherwise, we're not going to be able to get past this. So the way we do GPU is simple. Create a device. Usually you call it CUDA, because NVIDIA GPU use CUDA on top of it to program. So you don't need to know this. You can research that later. You move your model to the device, to the GPU. So this basically mean move all of the parameters, because those are tensor, to the GPU. That means any other operation that's happening with the parameter need to also be on GPU. So during training, we need to pass on the device so that we can move them. So in the training loop up here, I need to move my images to the device. And label to the device. And I need the device. Same thing for testing. Taking a long time, and as you can see, it's going down a bit more already, right? It doesn't stuck here anymore. So it's prevent underfitting already a little bit. Now the optimization we could do to improve this further is to make this set to none, to true. There's a few other things we could do. Is something about this. Let me search it up. There's a performance guide. So this article over here tells you everything you need to know. not everything, but enough to improve your code to run nicely on GPU. So I'm gonna look at my old code that I use. Where is this thing? This thing. Some of this I still don't understand, but you know, it work. There's a lot more thing I did, forgot. It is also a thing if you use their multiple GPU. So this GPU has multiple of them, but I find that this is faster if you use this GPU specifically. I think that's it. Yeah. Oh, loss.detach rather than .item. And then call synchronize later. So I'll do that, so that it doesn't have to sync between CPU and GPU all the time. That's just some nitty gritty. So I'll do that. Okay. Pretty decent. As you can see, it goes so much lower. Now, this is the cool part. Number of trainable parameters 23,000 compared to what we have 200,000, and that is a big difference, right? And even though it's a bit slower because it's on GPU, let's run this again on, did I just say GPU? Let's run it again on CPU. We have 30 hours, so I haven't used it much. Let's see. What else do we should we do? The Atom W might be better in this case. Oh, forgot to run. So run all of this except the last one. Just wait a bit. That's all the theory I can think of. So if you have any question, let me know. You cannot hear my mic. Oh, I was freaking out for a moment. Don't play like that. Everything is fine, right? Oh, okay. Beautiful. Okay. Yes, it's going. It's a bit faster, still slow. Still figure out how to optimize this, but that's fine. It's going down. The dense layer could not. We could try our best trying to optimize this, but no matter what, it will be so much worse than the convolutional neural network. Okay, so yeah, that was a lot. I know. What we could do now is do some submission, trying to submit this competition, because last time we did not do anything. Just a few things. Let's go to look at some important thing for now. Convolution neural network architecture. So image processing is such an important area in deep learning, is that they study, people research on this area already, and they found a solution. Not really exact a solution, but a bunch of way to improve it. And they pre-train it, bunch of model on something like a data set. So there's a big data set called ImageNet, and this data set contain 1,000, not just 10, 1,000 of different classes. So there are image of cats, image of bottle of water, and everything. And each of those class, there is a lot of images. So if in total there's about 14 million images, and that is crazy. And you try to train your model on this, that's not gonna go well with this GPU, even on this GPU over here. So people train it and they give you model already. So the one that I can remember and explain a little is something called ResNet. ResNet use something called residual. Let's take a look at that paper. Let's do some paper reading because we're cool. Maybe not, because this thing is confusing. So this is what their architectures look like. They have a bunch of convolution, right? And they figure out that this number works perfectly. Now you see this arrow over here. The arrow at the edge over here basically pass the input from here, reshape a little, and add it back to the output at this point. And that doesn't make any sense, but it is very important in this architecture. The reason being, you see all of these layers and all the way to the end, right? You see the fully connected layer, the dense layer here. But what's important is that the gradient descent, the formula we do the training, is that it's terrible with a large model, with multiple layers. And the problem is something we call vanishing gradient, is because the gradient all the way down here is so small, sometimes it's not visible for the model to update the parameter, right? So this residual over here, this stream, allow the gradient to flow all the way back very easily to train the parameter all the way down here. So this is the architecture they found out that works so well, and they train it on the ImageNet. They have the benchmark. So this is how paper usually goes. They have a bunch of experiments, some ideas and all that, and they give you some comparison with the other architecture out there, right? It's always the ImageNet. So if you go to PyTorch ResNet, you don't have to train your own model all the time if you need something simple. This is what you could do. You could load the ResNet model, a smaller version, just bigger and bigger, right? Pre-trained or not, doesn't matter which one. You load it and you can use it. That's it. On those 1,000 of images, 1,000 of classes. And there's something called transfer learning that you could do. Is that let's say you have this pretty, well, actually, you know what? Let's not do that, but we're gonna do something simple. I have the code from last night, so I'm gonna bother you try to go through this. Submission. So I did the exact same thing last night, try to make sure go through everything. I did create some submission. So this is what you could do. You could save your model. After you train it, you could save it, and then you could load it back as long as the model is in the same structure. And then you could apply it to a different input, sets of input, right? Get the prediction. I create the data frame out of that prediction. I submit that. I save that, and I get it at this location over here, somewhere over here. It doesn't show now. And then we could submit that file. So if we go to the competition, the digit recognizer, it doesn't have any price, but you could submit something. So if I go to file, this is my file that I did training from scratch, and if we submit, I got about 0.89 something score, and that is pretty decent, right? So let's take a look at the leaderboard, and you can see all of them are 1, and you wonder why and how they get that. Some of them, they might be pretty good at debugging neural network and they can get a good model out of it, but most of it, even for 0.9, if you take a look at some of their code, what they actually do is they use ResNet. They take the model, they do transfer learning. So because this model gives you a prediction of 1,000 classes, and those classes not numbered between 0 and 9, what you do is you cut off the last layer, the fully connected layer. You cut it off and you put it your own dense layer with 10 different classes. And then you freeze all of this convolution layer because it's already trained. It's already understand shapes. It's already understand a bunch of other things. So you freeze them, and then you retrain your model on the MNIST dataset, but you only train it in the last layer, and that is so much faster and it works so much better because now the last layer try to fit itself with the layer before, but also with the output, right? And there's only a single layer that need to be trained, and that is very efficient. So that is what we call transfer learning, and a lot of people just do that. They take ResNet, they transfer learning it, and then they submit it. Some of them got uh, a lot of like very high score. So that is what's happening, and it is possible. And from this point on, you don't have to train your model from scratch at all. You use one of this, do some transfer learning to fit with your task. So if you need something for capstone project or something else, this is what we usually do uh, to fine tune it to your task. I think that's it. We could go through the submission, but we already see that. What's important is the trial and error, but I don't think we have enough time. So if you have any question, comment, concern, please let me know. This is a lot. Let's save this. CNN, PyTorch. The naming is different. Alright, I'll upload this along with the video. ResNet look pretty cool and efficient. Exactly, yeah. There's also a lot of other architecture I could not find yet. Let's check that out. And I recommend everyone to take a look at the external resource on convolution to make sure you understand it, because this is tricky to get it in the first place, right? So I could not find the other resource that I usually look at. I got this useful stuff thing. That's not it. But yeah, that's not it. That's on graph. Never mind, don't worry about it. There's some visualization that people do. I don't know which one. Oh yeah, this is the exact same thing we talked about. Feature extraction from low level to high level until you can classify whatever you want, and it's pretty neat. So far ResNet is the one I know. There's also other one, but I don't know which one is the best exactly. But yeah, hope you learned something. Next week, I'm gonna go with something light, maybe something a bit more theoretical, trying to explain the concept of embedding because it actually there's something cool about this. Yeah, I think that's it. Thank you guys for coming. It's pretty awesome.